Logarithms are a useful tool to be able to understand the magnitude or ratio of something. They are the inverse of exponents, and they're convenient because they allow us to be able to express really, really large or really, really small numbers in a simplified way in the form of a magnitude relative to its base. So the word logarithm is of Greek origin. The first part, log, is meaning logos, and that means ratio. So we can think of that as magnitude, and arithmetic, that is arithmos, and that means number. So logarithms really allow us to be able to see these numbers as magnitudes. So for example, if we have log base 10, we can express 1,000. We know that's the same thing as 1 times 10 to the 3. So that's 3 places to the right of 1, so 3 zeros. So we're able to express that log base 10 of 1,000 is equal to log base 10 of 10 to the 3 is equal to 3. So you can see this is basically asking how many magnitudes of 10 are in 1,000. So we know 10 times 10 is 100, times 10 is 1,000. So there's 3 magnitudes of 10 within 1,000. So this is the base and this is the number. So we're trying to see how much of the base goes into 1,000. Similarly, we can express a small number if we have 0.001. So now if you move 3 places to the left of 1, 1 times 10 to the negative 3, we can have that as, again, log base 10 of 0.001 is equal to log base 10 of 10 to the negative 3, and then that's negative 3. So basically it's asking how many magnitudes of 10 are in this number. And so we're able to express these as a magnitude. And so that's the same thing as saying how much you have to move to the right or to the left of 1 to get this number. So if it's a positive exponent, you're moving to the right of 1, so we have 1, 2, 3, and that's why the exponent is 3. You have 3 zeros, the number of zeros is the same as the number of exponent, it's the same as the exponent. But if you're moving to the left, the number of zeros is less than that, because remember you have to move past that 1. So anything, whenever you're moving to the left of 1, and it's a negative exponent, remember that you're going to have 1 less 0, because you have to move past that 1. So again, negative 3, you move 3 places to the left, and if it's a positive number 3, you move 3 places to the right of 1. And this is all with reference to 1. Even if this 1 isn't there, 10 to the 3, you can put that 1 there and imagine it as 1 times 10 to the 3, you're moving 3 places to the right, 1 times 10 to the negative 3, you're moving 3 places to the left. And if you want to imagine the number of zeros when you're moving to the left, it's 1 less 0, because you have to move past that 1. If it's a number greater than 1, you're moving to the right, and it's a positive exponent. Number of zeros is the number of places. So you can easily say something like 10,000 that has 4 zeros, so you know that log base 10 of 10,000 is 4, or you're moving 4 places to the right of 1. And so this is really useful to be able to quantify big or small numbers again. So let's just put that in terms. So again, log, this is our base. So you don't always have to use base 10. We can use different bases, but most commonly we use base 10 because it's easy, it's applicable to many situations. And so we ask how much of this base is in that result. What magnitude, what power do I have to raise this base to get this result? And so this is how we express that. Log base of that result is equal to the power that we get. So this is basically the reverse of exponents. And saying what power do I have to raise this base to be able to get that result? So let's say I have base 10 and I want to get to 1,000. What power do I have to raise 10 to be able to get to 1,000? And the answer is 3. And so log base 10 of 1,000 is 3. So 10 to the third is equal to 1,000. So you can see how this is the reverse of exponents. And let's say not log base 10, but we have log base 8, and this result is 64. So what power do we have to raise 8 to be able to get to 64? Well, the power is 2, because 8 times 8 is 64. So we have to raise 8 to the second power to be able to get 64. So our power will be, in this case, 2. So log base 8 of 64 is equal to 2. So it's easier if every time when you see a logarithm, you're thinking, what magnitude of base do we have to get to be able to get that result? So what power do you have to raise that base to be able to get that result? What exponent do you have to raise this base? What magnitude or extent of base is in this result? And so that's basically what logarithms are. And there are also a couple of logarithm rules that are useful to know. And 3 of these, actually, you can tell by looking at the exponents. So any log base system, log base 8, log base 3, log base 10, log base 9, any log base system of 1, we know that anything to the power of 0 is equal to 1. So log base 9 of 1, what power do you have to raise 9 to be able to get to 1? The answer is 0. What power do you have to raise log base 10 of 1? What power do you have to raise 10 to be able to get to 1? The answer is 0, because anything to the power of 0 is equal to 1. So if I said log base 3 of 1, well, what power do you have to raise 3 to be able to get to 1? The answer is 0, so this is 0. What power do you have to raise 8 to be able to get to 1? Again, the answer is 0, answer is 0. What power do you have to raise 10 to be able to get to 1? The answer is 0 is equal to 1, so answer is 0. So as we can see just by looking at the exponents. Similarly, you can see this too. What power do you have to raise 10 to be able to get to 10? What power do you have to raise a number to be able to get itself for any log base system? Well, the answer is 1, and that's with anything. Log base 8 of 8 is equal to 1, so anything to the raise of the first power is itself. Similarly here, what power do you have to raise 10 to be able to get to 10 to the third? What power do you have to raise this 10 to be able to get this? Well, it's just 3, because 10 to the 3 equals 3, so again, you can just think about this canceling out, or just think about what power to raise to this to be able to get to this, and that's 3. And so this is also a useful rule to know. So whenever you have your base and this is the same, if this is the power of something, these sort of cancel out each other, and you just get this, so you just get 1,000. So those are pretty useful rules that you should know, and these 3 are also very important. So log, we're able to turn basically multiplication into addition, division into subtraction. So anything log base a times b, that becomes log a plus log b, log a divided by b, that becomes log a minus log b, and this as long as the base is greater than 0 and not equal to 1, you can do a neat trick where you push this exponent to the front. So just push this to the front, and then you can have 3 times log base 9 of 10 in this situation. So you can just really quickly just push this exponent to the front, and so that becomes 3 times log base of 9 times 10. And it doesn't really matter whether these 2 are the same, or if they're the same, it'll just be equal to 1, it'll just be equal to itself, obviously. But if the base is different, or if the base is 8 or 10 of 10, or base of 7 of 10, that doesn't really matter. But even if the base is the same, even if this is 10 of 10, you know that from this rule that would just equal to 1, and it would just be equal to 3. So but anyway, this trick is really cool. As long as the space is greater than 0 and not equal to 1, you can push this exponent to the front. And those are the logarithm rules that you should know. So again, just want to emphasize this one more time. So this is asking how many magnitudes of 10 are in x, or how many multiplications of 10 do we need to be able to get to x. So let's say if we have log base 100, And if you don't have this base 10 here, we can just, when it's not written, we just assume this is base 10. Anyway, this is equal to 2. Because why? Because 10 to the second is equal to 100. And if you want to think about the number of zeros, remember 10 to the second is the same thing as saying 1 times 10 to the second. So that's basically moving 1 and then moving it 2 places, right? And so that's just 100, right? And so if we have, similarly, if we have log base 10 of 1000, it's how many multiplications of 10 do we need to be able to get to 1000? That's equal to 3. And so that's basically the same thing again as saying 10 to the what power is equal to 10 to the third. And so we know that obviously n is equal to 3. And so that's what this is. And so again, it's how many magnitudes or multiplications of 10, what power or exponent of 10 do I need to be able to get this number. So all logarithms are, again, is magnitudes. For logarithm of 10 to the 4, and obviously that's 4. And if we want to do a negative exponent, however, log base 10 of 0.0001, that's 1, 2, 3, 4 places to the left. So that's log base 10 of 1 times 10 to the negative 4. Remember, there are 3 zeros because we're moving to the left, and 4 places, so negative 4 to the left. So 4 places to the left, that's log of 10 to the negative 4, and that's just negative 4. And you can also express this as log base 10 of 1 over 10,000. Because remember, this is the same thing as 1 over 10 to the 4th, that's equal to 10 to the negative 4. And so express that as that. Based on your log rules, you know that if you log a over b, if you flip these, you can actually put the negative sign across. So if you do log 10 of 10,000 over 1, you're flipping them. So remember that's saying this is the same thing as log of a, log of 1 minus log of 10,000. And so if you flip them, you're basically doing log of 10,000 minus log of 1. You can put a negative sign out there. And so you can do this. You do negative log of 10,000 over 1. Again, this is log of 10 to the 4, so that answer is 4. You have your negative sign, so you still get negative 4. So you can think about it either way. You can just think about it this way, negative exponent 10 times 10 to negative 4, you get negative 4, or you can think about it this way, you're flipping them, putting the negative exponent in the denominator, and then you're flipping this and then putting the negative sign out front, and so then you get negative 4. So whenever you flip numerator to denominator, if you flip your numerator and denominator, you can just put a negative sign because of your log rule. So that's a really easy rule to be able to just shift negative exponents to the denominator to make it positive, and then again, you can flip it again, and then your negative sign out front, and so forth. So again, just whenever you have logs, just think magnitude. What magnitude of 10 do I need to get 1 over 10,000? What magnitude of 10 do I need to get 1 over 10,000? What magnitude of 10? The same thing. If you flip this, what magnitude? Then you put a negative sign out front. Then you can say, what magnitude of 10 do I need to get 10,000? That is 4, and then you just remember that negative sign. And so why do we have logarithms and where did they come from? And later I'll show some examples of why they're useful in the real world and representing magnitudes in a number scale. But the original use of logarithms was actually to be able to convert long multiplication problems into simple addition problems. And so what people had is they had these log tables, and they could turn long multiplication problems. For example, if you want to multiply 3,396 times 4,656, you can imagine that it would take a long time to be able to write out that calculation by hand. But with log tables, they could simply look it up, and because logarithms essentially turn multiplication into addition and division into subtraction via our exponents, they can easily, it's much easier to be able to add something than it is to be able to long multiply these numbers out. And you can look up which exponents to be able to add. And so logarithms were actually invented in the 1600s by the Scottish mathematician John Napier. And he did it between 1594 and 1614. And the reason he did this is, again, to be able to simplify these calculations. And so eventually Henry Briggs, he compiled the first log table so that we could be able to simplify these tough calculations without a calculator. And so you have to know that this is a time that's before calculus, before Newton's, before Leibniz, before Gauss. And so we didn't have calculators, of course, and we needed a way to be able to turn these multiplication problems into addition in the 1600s. And so I'm going to upload a separate, more expanded video on these log tables and an example of how these numbers are obtained from these log tables and how we use this multiplication and convert this multiplication into addition. But basically, this is how they do it. So if you have 1 multiplied 37 times 59, you would just express this as in the log base 10 system. So you would say 10 to what power do I need to be able to get 37? And similarly, you would do the same base. You would say 10 to what power I need to get 59. So using that same, because it's the same base, you can add these exponents, and then you would search this up number in your log table, and you would get 2 plus 183. So basically, this is how they would convert this multiplication problem into addition via exponents. And you could look up these exponents, and I'll show how they looked it up in the log table in the more expanded video. And so that's how these log-based tables work. But nowadays, yes, we have calculators, and we don't really need logs for this purpose necessarily, but logs are still useful for to be able to express the magnitude, or scale of something. And so it's really helpful to be able to think about logs in this idea of magnitude of it being a scale of something. So most commonly we use log base 10, and in the real world, it's really helpful to be able to express the magnitude of something as a scale, as a number scale. So for example, we can express the magnitude or brightness of stars and compare the brightness of each star as a log-based number scale. We can have the Richter scale, which we use to quantify the magnitude of earthquakes and be able to compare the magnitude and severity of earthquakes. We can have the sound scale and compare the magnitude of sound as a log-based number scale. And we can really see the usefulness of the log-based scale when we look at the pH scale. So for example, we're quantifying in the pH scale the amount of hydronium ions, or the amount of H3O plus or H plus ions in solution. And we quantify that as a concentration, as moles per liter, as molarity. And so we're looking at the amount of hydronium ions, and we look at that as a number scale ranging from 0 to 14. But what we're really looking at is we're looking at concentrations of hydronium ions ranging from 10 to the negative 14 to 10 to the 0. So as you can imagine, this is a really, really small number to be able to express 10 to the negative 14 as 14 places to the left of 1, or 13 zeros. That's painful to be able to, or it's harder to be able to write 10 to the negative 14 or 14 places to the left of 1 with 13 zeros to the left of 1 every single time. We want to be able to express this as a simple number scale ranging from 0 to 14 as a pH scale. So what we do is we take the negative log of the hydronium ions in solution. So we can express this really, really small number as a whole number, as an easy to read number as a pH scale. So we can see that actually the log of 10 to the negative 14 would actually give us negative 14, but in the pH scale we have a positive scale ranging from 0 to 14. So if we set up the pH scale, instead of taking the negative log of the hydronium ions, we just took the positive log of the hydronium ions, we would have a pH scale that ranges from negative 14 to 0. So negative 14, negative 13, negative 12, all the way going up to 0. But it's easier if we look at the pH scale as a positive scale. So what we do is we take the negative log of hydronium ions in solution, and we quantify the concentration of hydronium ions in solution. So for something that's pH 14 has 10 to the negative 14, we take the negative log of 10 to the negative 14 so that we can obtain the positive number 14. And so we get that exponent, and we can quantify a really low amount of hydronium ions, 10 to the negative 14 molar hydronium ions, as pH 14. So it's really basic, it's alkaline, we're quantifying the magnitude of hydronium ions. Versus if something like pH 2, that's 10 to the 2, we can 10 to the negative 2, we can quantify that as having a higher amount of hydronium ions. So you can see as we increase in pH, we're really decreasing the amount of hydronium ions, but as we decrease in pH, we're really increasing the amount of hydronium ions. And it's opposite, because the pH scale, P meaning negative log of, is a negative log scale. And so we take the negative log of a concentrations ranging from 10 to the negative 14 to 10 to the 0 to obtain our pH scale ranging from 0 to 14. And you have to understand that moving up or down the pH scale, even by 1 pH, is not trivial, because we're really moving by a magnitude of 10. So for example, if we move from pH 5 to 6, we're decreasing the amount of hydronium ions in solution, the concentration, by a magnitude of 10. So that's not trivial, that's not a small change. Similarly, if we move from pH 10 to 9, we're increasing the amount of hydronium ions in solution. So if we go from pH 10 to 5 again, we're increasing the amount of hydronium ions in solution by 10,000x. So there's 10,000 as much concentration of hydronium ions in solution in pH 5 than there is in pH 10. And so moving up or down the pH scale isn't trivial, because this is a log-based 10 scale. We're really moving a magnitude of 10 every time we move up or down the pH scale. We're really moving a certain magnitude of 10 every time we move up or down the pH scale. So I hope that was helpful. In the next video, I'll go over how to visualize these log functions and how to estimate these log values through mental math. That will be really helpful for the MCAT.